Hi, thanks for coming out here for this talk. So my name is Mikola. On GitHub, I'm at Mikola Lysenko. So here's my profile. I currently work at Bits Cooperative, which is a worker-owned co-op based out of Hawaii. And today, I'm going to talk about numerical computing. So I'm going to start with these clip art images here. So just bear with me for a moment. So each of these images is illustrating something that might be, maybe considered a hot or extremely exciting emerging area in computing of some sort. So we have things like augmented or virtual reality, data visualization, distributed manufacturing, 3D printing, deep learning. And the one thing I want to draw everyone's attention to with all of them is that a critical component for each of these new or emerging areas is numerical computing. Right? So what is numerical computing, right? And why should you care about it? So there's maybe a couple of different ways to look at it, but broadly I would say there's two main ingredients to it, which is computing with large arrays of numbers. So like computing with a bunch of numbers like tensors or arrays or matrices, and high performance numerical algorithms that would operate on these giant tensors or n-dimensional arrays. So another way to think about this is it's calculus and linear algebra with computers. And this is important because it turns out, recent advances in everything ranging from natural language processing to computer vision are all built on fast computations using these giant arrays of numbers. And so why do this all in JavaScript? So that's like the second part of this talk. So the main reason is you want to do this on the web, right? So at the moment, the web is pretty much the last major application platform which isn't controlled completely by some private company. So if you want to actually go out there and build things and get them directly to your customers without having to go through some intermediate app store, the web is the only show in town. Also, the web is great for creating accessible explanations. So I'm going to pull a slide out here from Brett Victor. And so these are a collection of different visualizations which all run on a client, illustrating different concepts. So for example, this one shows how you can understand segregation in terms of processes like objects moving from one place to the other. And if we would like to create these sort of data visualizations and allow them to run on a client and allow people to interact with them, then we need to be actually running the simulations on the client. So we would like to be able to take modeling or computation that we would do in some backend environment and move it to the front end, so then people can change different parameters and see how it works and then learn something from that model. And then finally, JavaScript has the largest and most active development community in the entire world right now. So we have all of these capabilities with numerical computing that are available to us, and we would like to make it more democratic and accessible so then more people can pick these things up and start doing something with it. So we would like to have people grab these advanced computer vision or numerical algorithms and take them and put them into their browser. So that's sort of a high-level view for what this talk is about. So I'm going to now give a couple of examples of numerical computing on the web in a browser. Right? So here is, for example, an elastic wave that can be simulated. So you can do things like physics simulation running in a browser. And this is all just WebGL, like running on a client. We can do things like 3D modeling. So I can use my browser here to generate some little shape using GLSL. And I can render it here, and then generate a mesh from it, and then zoom in and out. I can also create creative audio reactive visualizations. So this is actually reading input from the microphone right here and then rendering it. So this is also using some numerical components. This is another demo that I've made. So this is actually some neuron data, which has been taken from mouse brain. And so I can adjust these little sliders here and then render this volume in real time and do different processing on it completely in a web browser again, right? So this is all just running in JavaScript on here. And then last, I can do things like deep learning in a web browser. So this is a standard MNIST benchmark, and I can draw a digit, and then a neural network which is running in my browser right now is actually reading these symbols and then using it to convert these pixels that I draw over here into digits, right? And this is all happening in JavaScript on the client in my web browser, right? And we can also see more advanced examples of this using things like keras.js, which allows for fancier models to work in a client. So we can do this today, but it's a little awkward right now. So all of these things require a bunch of hacks to make them happen. And the reason is that JavaScript is missing a bunch of features which we would want to have in a language that would be better suited for numerical computing. So we don't have things like operator overloading, which makes writing all of this stuff extremely cumbersome. We're also sort of barred off from using large function or some of the native capabilities like SIMD or vector instructions, which would allow us to write faster code. Also, JavaScript doesn't have a concept of threads, so we can't use multi-threading. And we don't have things like typed objects or values, so memory management becomes very difficult in JavaScript. But that said, though, these are not unique to JavaScript. So Java is also used in many cases for doing this and has the same exact problems. Similar problems exist in Python and other languages, which have also been successfully used for doing numerical computing. So in Python, you still have things like a global interpreter log, right? So that we have these language problems is not insurmountable. We can still get stuff done. But there are other issues in the broader ecosystem, so we don't have something like a standard multi-dimensional array data type in JavaScript, and so we have to do a bunch of data conversion from one format to another, which is inefficient and slow. We also have problems with native bindings in JavaScript that are not present in other languages, and there's also this larger cultural inertia in the numerical computing community and in the JavaScript community in order to get people involved in actually doing stuff with this stuff. So these are the sort of problems that we have to overcome in order to do numerical computing in JavaScript. And there is some progress on them. So on these first points here for the operator overloading and SIMD stuff, there is progress right now in ES7, the next iteration of JavaScript, and in the TC39 community, or the TC39 to ultimately try to fix some of this. So I have some faith that that will ultimately get done. And these other issues are things that we can actually solve ourselves in user space without having to go all the way to the level of some standards board. So let's go now into some details for how we might be able to solve this, or a possible set of prescriptions for these problems. So the first is multi-dimensional arrays. So the current state of JavaScript is we have a bunch of different approaches. The one which I've seen most commonly adopted is perhaps this arrays of arrays technique. So the idea is that you want to create a multi-dimensional array, so you just make an array of arrays and just do that recursively however many times in order to go, create your n-dimensional array. The problem, though, is that if you want to access an element of this array, then you have to do as many levels of pointer indirect lookups on these arrays as the dimension of this multi-dimensional array. And each of those, if your arrays are sufficiently large, is going to be a cache miss. And so you're going to end up wasting as many as the dimension of the array you're looking at indirect pointer accesses in order to get to the cell that you're looking at, which is pretty inefficient. Also, you have to store all these extra pointers to all these other array objects, and so that requires n to the d minus 1 extra space. And if you do a traversal of this array, because you have all these indirect cache lookups, you're basically paying this extra, d times n to the d traversal, right? And if you want to make a copy of this thing, then you just have to go through and slice all the pointers, which is really slow. So arrays of arrays are actually this is just laughably inefficient. So if you were writing in something like C or Fortran, you would probably do it like this, right? You would just take a regular flat array or a typed array if you were doing it in JavaScript, and you just lexicographically flatten the entire array out. So the advantage to this is that you're not wasting any extra space, right? Like there's none of these extra pointers spinning around. If you want to access anything, it's just immediate. And even better, when you do a traversal, you're actually going to, if you scan the traversal of this array in lexicographic order, you don't have to do all these extra indirect memory accesses, so things will actually scale with the size of your cache lines on your processor, which is a very big deal because oftentimes the size of those cache lines can be very big and probably much more than the number of cores on your computer, right? So, writing algorithms that take advantage of cache performance is generally a higher priority than even parallelizing them or running them on a distributed system, right? Because this is how you get the really big scaling of performance. So that's great. And also, to some limited extent, you can still sort of slice an implicit array by basically changing the size along the largest axis. So This is commonly used in many numerical codes, right? But there's also an even better way where we could generalize this a little bit. So one problem is if our matrix here, if we basically flatten it all out in lexicographic order, then we'll get one ordering, but we could also flatten it in row major or column major order, or do it in some different way. So we can generalize this using this concept of strided arrays. And so in a strided array, what we do is we keep track of basically the shape of the array, and then we also store an offset pointer into the array and a stride vector that tells us how far we can step through it. So this has all of the same benefits as an implicit array, except we can now do slicing much more efficiently. So for example, if we wanted to transpose this array, all we have to do is just switch the two stride components, and then we've transposed it in place, and we don't have to do any work. Or if we want to take, say, just the first row or the first column, we can just cut them using one of the stride vectors by itself. So there's a much more flexible representation for creating arrays or matrices. And this is what's commonly done in systems like Julia, MATLAB, or SciPy arrays. They use these sort of strided arrays. So I propose, for basically the purposes of creating some standard format for JavaScript, we could adopt an Ende array format, very similar to the way that Python does things, by basically creating a standard object. And all we have to do is give it 3 pieces of information. So we have the underlying data array. We have to store the shape of the array, so basically the linear dimensions and extents, a stride vector that tells us how these are arranged in memory, and an offset. Right? And so with this data, we can now store and pass around these strided multidimensional arrays, and then just create libraries that can either produce or consume these objects. Right? As a reference implementation, I have this module that I've written called Ende array, which basically does just this. So this is a set of tools and also some convenient methods for working with slices. So to give a quick overview of that, we have things like slice operations, so you can cut out a subarray using this .high and .low syntax. Transposing, different stepping, so you can do things like downsample array by a factor of 2 by just multiplying the stride by 2, or selecting subarrays, like picking out a row or a column or some component of a tensor. And each of these operations is essentially, it's basically constant if the dimension is fixed, and they can be chained together using a fluent notation. So you can, write something like select a region by doing .high, .low, etc. to cut out some subarray. Okay, so that's the first part of numerical computing. So we just have to pick some multidimensional array format, and then we need to start creating algorithms that can produce or consume these arrays. So in terms of creating numerical algorithms, there's a couple of big approaches, but I would say they sort of broadly break down into 2 categories. The first is we can try to just implement everything in JS, and this is probably the only viable option today. And I have some partial work along these lines through Sci.js, which is a collection of modules that can either produce or consume Ende arrays. There are something like 130, 150 of these, and they can do everything from some basic linear algebra to image processing and Fourier analysis for audio and video processing. So this is a start. Let me go close this tab. Right. Oops. Shit. Okay. Accidentally closed my slides. Sorry about that. So we have Sci.js, which is one project that does this. We also have Compute.io and stdlib, and also systems like WebBlast. So we have some partial results that all can produce or consume Ende arrays. And also WebBlast uses components from Sci.js and is also used in Keras.js too for the deep learning. So there's a number of these different results, right? And so this is basically the state of the art right now for doing numerical computing on the web. But in the future, we would like to go further with this. So if we think about systems that have been successful in the past in this space, the biggest names are probably things like SciPy or MATLAB or R or Julia or things along those lines. And I would say that most of those systems can be described as basically Fortran wrappers. So to bootstrap something like SciPy or MATLAB, the standard practice is to just grab an existing Fortran set of libraries and then just wrap them all up in some idiomatic API for whatever language you're working in. So SciPy is really just a bunch of Fortran and C routines that have all been packaged up and exposed to Python. So then you can use Python to script and drive these computations. So if we want to be able to get caught up to these other systems in JavaScript quickly, we need some way to bring that existing native code into JavaScript efficiently. So one way we could get something working right now is we can use Node native modules. And there are some partial efforts along this, but up until recently, and even to this day, maintaining native modules in JavaScript with Node is extremely difficult. It's very fragile, things break all the time, it's a ton of work to keep it up, and you have to just babysit these, and because every version of Node or Electron or whatever on every different platform breaks compatibility. So it's difficult to publish and maintain native modules. There are systems like Asm.js, but these have issues with load time because parsing all of the JavaScript from this native code is difficult, and then also as a foreign function interface, you end up wasting a bunch of memory because you have to spawn multiple instances of the library and they each have their own separate heaps, so it's technically difficult. In the future, WebAssembly might be a better solution, but it's still not viable as a spec, but this might give us some other options. And perhaps even more ambitiously, if this does become something that is a high enough priority for the web, we could eventually get web APIs standardized through either like the W3C or some other standards process, and actually get browsers to adopt and implement this, which would be amazing, because then we wouldn't have to be shipping and re-implementing all this stuff in JavaScript all the time, and we could actually have the vendors compete to get the best possible implementation for whatever native platform. So that would be the dream, but none of these are easy solutions, so we can't easily grab stuff and pull it off the shelf. But none of these are also impossible, though. So these are all things which could be done right now and we can be working on, and there is some partial work along those lines. So I guess in summary, numerical computing is important. It's something that we should all try to work toward bringing to the web and to JavaScript. And I think in terms of 3 concrete things that we can do for trying to make this happen, the first is that we should start advocating for better standards and improvements to the systems that we are using right now. We should also try to grow the module ecosystem so this becomes viable and then people can actually use these things and start doing stuff with it. And then finally, we just need to start building more stuff with it because we already have some pieces out there that work, and so we just need to start creating more things and getting more people interested in it and start getting numerical computing working on the web. So I think with that, I'll wrap this up and leave this open to some questions. I'd also like to acknowledge many of my colleagues who have been helpful here. So Ricky Urser, Jasper Van de Grond, and then Ethan and Philip and Eric Arnebach and Michael Rogers, who is very gracious in bringing me out for this thing. And with that, I'll leave this open for questions, and thanks.
Anybody have a question?
So there was talk often about ES plugins.
Mm-hmm.
Is that related to this effort? Is that parallel, tangential?
So I actually don't know much about ES plugins. I think, was this related to, there's been a couple of attempts to create a standard system for native modules. And I would say that I am at some level personally not too attached to any particular one. I just want something to exist, right? But we need that, right? And I think if we have that, that's going to make it a lot easier to do numerical computing. So.
Any other questions?
I'm just curious about your thoughts that Node is best known for its I/O, not so much compute-intensive stuff. Do you see that as being a problem, trying to grow interest in doing more numerical stuff through Node?
Yeah, that's a good question. And I think I would say that I don't actually see that as a problem, and I would actually say that the I/O capabilities in Node are a great asset in some ways. In terms of raw compute power, if you look at other languages that have been very successful in numerical computing, like Python or MATLAB or R, none of those languages are actually that good at computing. In fact, in many ways, JavaScript is actually a far better option for writing compute-intensive applications than Python. The only reason, and it's purely a historical accident, is that Python just happened to be there at the right place in time, that basically when people needed to start looking for something other than MATLAB, the community was able to mobilize and fill that niche. So I don't think that any of the things that people often would say, like JavaScript is not good for computer or whatever, are remotely applicable here. It's totally an issue of cultural inertia. There's just all of this work that is still getting done and built in Python, and it just continues to get, it just grows in there, right? But the compute bottleneck isn't really an issue, right? Because in Python, when you write these things, you're typically calling out to native routines to do all the heavy lifting. And that heavy lifting is where you are basically going to be burning all your cycles. So it's stuff like a giant matrix multiply or matrix vector multiply is where most of the cycles get spent. And if we basically push that down to some low-level, highly optimized code, we can do all the same stuff in JavaScript that they can do in Python. So I don't see it as a problem.
Any other questions? Good. All right. Thanks, Mikola.